So in this video we're going to talk about electric fields, and we'll draw electric field lines and be able to calculate the electric field strength. So the title for this slide is Electric Fields. I asked you in class what an electric field is. We know that it is an area around a charged object where another charged object will feel a force. So if I have a charged object here, a negative charge, we know that the field line's coming in towards a negative charge. That means anywhere around this area, if I placed a test charge, we normally place a positive test charge. So if I place a positive test charge here, he will be attracted to this. That's why the arrows are pointing inwards. If I had another one here, a positive test charge like this one, and we know the field lines are going out, and that means what I can do is anywhere at all here I can put it maybe further away, it doesn't matter. The point is, he will feel a force repelling him. He will run away. If I place a negative charge here, of course, this is the opposite. He will be attracted to it. So this is the whole idea. It's the space around it where you will feel an electric force because of the charge that we're talking about. Okay, and we did the field line patterns. When we bring two charges close together, we have a positive and a negative. We know that they go from positive to negative. It looks a bit like a magnet. If we have a positive and a positive, they repel each other. So you'll see in the middle, the forces will cancel each other out. There'll be nothing in the middle. That's going to be important for this question here. If you look at this question, we have three charges, A, B, and C. You want to rank them from strongest to weakest. So A is closest to this charge. Whether it's positive or negative, it doesn't matter. The point is, it is a test charge close to this one. Because it's closer, it'll feel the strongest force. As you know, Coulomb's law, it's inversely proportional to the radius squared. Not important for now, we just need to know that A is the strongest because it's the closest. Easy. B is further away, so it'll be weaker than A. So A is stronger than B. And finally, C, as I said earlier, this is going to end up being zero. The force will cancel each other out. So this is actually zero. So that is all stronger than C. So this is the correct ranking. Also, if you have two charges and one charge has more than the other one, you will have to draw more lines to show that this has stronger field lines. Over here we've got a lot of field lines coming out, but in Q there's only a couple going in. That's why you do when you have your bigger charge and a smaller charge. There are some rules that you need to know to draw. You know that is, of course, positive to negative. We know that attraction, you will connect the lines together. So if you have a plus and a minus here, you have a field line coming out, this one's going in, you will just connect the lines. It will look like that. Okay, this is a minus. Repulsion, diverging lines, which of course I've done with you as well many times. The field lines will go up and away from each other, or down and away from each other. Either way, they will repel each other. These are both positive. Number of lines is proportional to the charge. More lines, stronger charge. Okay, and they never cross. These field lines never intersect with each other. They have their own path. So if you wanted to find the force from an electric field, we can do. An electric field, we know, is the amount of force that a test charge will feel. So we will have a formula which involves the force. E is force over the charge, right? The force that a test charge will feel. E equals F over Q, or otherwise known as FEC. This is the rule that we can use to calculate the force on this charge, or even the electric field if you already know the force on the charge. Okay, so a positive charge will move in the same direction as a field. We have the field line going to the right. We have a field line here going towards the right. That means one side is positive, the other side is negative. Electrons will do the opposite. The electrons will go towards the positive. They'll be negative because they're in the opposite direction. Okay, we did a practice question together. We had a charge in a field with this magnitude. It feels a force like this in the same direction. That's important. What is the sign in magnitude? The easy part, magnitude. Let's calculate the magnitude. Q is F over E because we're trying to find the charge. The force 0.45 divided by 6.1, and you get the value here. And you need to know if it's going in the same direction, if it's positive on one side, negative on the other side, doesn't matter if it's down and up or right and left. If it's in the same direction, it's going from positive to negative. So it's attracted to the negative side, which means it must be a positive test charge. Okay, So now we can calculate the field due to a single point charge. This is how we get the E formula, the slightly bigger one, by using Coulomb's law. We know E is F over Q. Instead of F, let's put in Coulomb's law. Let's do K Q1 Q2 over R squared. We put that in and we realize that there are two Q's that can be cancelled. One is capital to show that it's two different Q's. So one of these Q's will cancel, and that leaves us with E equals KQ over R squared only. That is how you can find the electric field around any test charge, or any point charge, I should say. Okay, so we did some practice questions. Here we wanted to find the magnitude of electric field produced by a 1 microcoulomb point charge at that distance. We solved it, KQ over R squared, and we did 9 times 10 to the 9, multiply that by 1 times 10 to the minus 6, divided by 0.75 squared. This 9 times 10 to the 9, remember, that's K. That's a constant. That number never changes. That's always there. K is always this. And you get 16,000. We did another example. This was a silver example. It's a little bit more challenging. Now that you have two test charts, what are you supposed to do? Well, what you can do here is you calculate the electric field for this one. Okay. Then you can calculate it for this one. And then you do the resultant using Pythagoras. This one is pushing up, this one is pushing to the right, which means they will tug along the diagonal axis. We did this when we did the adding vectors. If you have an arrow going up, and then you have an arrow going to the right, like this, you join them tip to tail. So you can end up doing this. It's the same thing as going up, and then from here going to the right. And that is the final point, that's the starting point, and that means my displacement is in this direction. Okay, so we solved it. What we did was we did the E1, KQ1 over R squared, K, 9 times 10 to the 9, Q1, 5, 10 to the 10 to the minus 6, over 0.75 squared, and we got 80,000 newtons. We then looked at the second one, and we realized the numbers are all the same. The R is the same, and the Q is the same, the K, of course, is the same, so the same number. So then I can simply use Pythagoras. We've solved this one, and we've solved this one. We can find this one, yes? We can do this, directly go straight to the Pythagorean theorem, which is the square root of this squared plus this squared, and that gives you the answer. If you wanted the angle, you can easily find the angle by doing tan opposite over adjacent. We use tan of the angle, yeah? Tan minus 1, and in this case, this is my opposite, this is my adjacent, hypotenuse. O over A. Doing that, and you get your angle. And the last question here was that we have two test charges placed, and we have a point P, the field is going up. We know already that a field line will go from positive to negative. A field line goes from positive to negative. This one should be positive, this one should be negative for that to be true, because this is going upwards. Of course, if I draw it going around like this, it will be going still in the upwards direction, because this arrow is going like this as a vector. So it's going like this, up at this point, and then curving to the left. Same thing here, it's going up like this, up at this point, and then curving to the left. And that has given away the answer already. Let me erase all of that. And we solved it. Yeah? We found out this was a bit harder than the other one. So now we know that this one here should be, the answers are right here. Charge Q1 is negative, Q2 is positive, this is minus, and this is plus, just like I mentioned right now. And finally, the path of a charge in a uniform field. You just need to know that if I place a charge, a positive charge, inside these two plates, it will accelerate towards the other side. Positive will go towards negative, negative will go towards positive. It will accelerate because there is a force. And if you remember Newton's second law, F equals ma. So that means it will accelerate. Same idea, if it's going towards the right, what will happen is it will curve towards the left. This one will end up curving towards the right, depending on the strength of the charge or even the strength of the field. Thank you.